All right, section 12.5, we're going to take a look at arc length, which we've seen in a couple different situations before. We're going to look at another one today, and then curvature, which is a new idea entirely. So I'd like for you to recall what arc length looks like in 2 dimensions. So in 2 dimensions, arc length is the integral from a to b of x prime of t squared plus y prime of t squared. Okay, so that's what we just did in a previous lesson. And if we're going to take a look at arc length of a space curve, then we're looking at this same thing but in 3 dimensions, right? So if C is a smooth curve given by the parametric equation R of t, which is x of ti, y of tj, z of tk, on the interval from a to b, then the arc length of C on the interval is the 3-dimensional version of the one we just did. Right, so we have x prime of t plus y prime of t plus z prime of t. And this is the integral from a to b of the magnitude of r of t. Okay, so those are 2 versions of the same equation, really. So we're going to do an example. We're going to be looking at a vector valued equation because we're back in chapter 12 now for this section, right? Vector valued equation. And so it's an equation, in this case in space, so it's got the 3 components, and we're going to find the arc length. So here's our vector valued equation. So we have the components 4 natural log of t, t squared, and 4t, and we're finding the arc length. So the arc length, according to the formula we just looked at, is going to be, and they always use that lowercase s, is the integral. And we're going to do this on the interval they give us, which is 1 to 3. And this is the square root, and it's the derivative of each of these pieces squared. So what's the derivative of 4 natural log of t? 4 over t. And then this will be squared, plus. What's the derivative of 2t? I didn't say that. 2t is the derivative. What's the derivative of t squared is what I meant to say. So 2t squared, giving you the answer as we go. How about what's the derivative of 4t? That one's 4. All right, so it looks like this, right? All good? Okay, so we're going to clean this up, see what simplifies, and maybe if something doesn't, figure out what we do next. So we're going to have 16 over t squared plus 4t squared plus 16 dt. Now, as we've encountered, sometimes you can factor these things and sometimes you can't. This one you actually can. It actually does factor. You might be looking at it though and saying, I don't see how in the world the way that it's currently written. So give me a couple just steps here to rewrite it in a way that's a little bit easier to look at. To start with, it might be helpful to have the t squared term at the beginning and to have the one that's over t squared at the end. And that would put the 16 in the middle. If you don't like the 16 and all of that, you could factor that out. That would certainly be a possibility. At least you could factor 4 out of all of it to see what that would look like. So if we factored a 4 out, we could even just bring it out in front like this. So this would be t squared plus 4 over t squared. That squared goes over the whole thing, including the t squared. And this does factor. So if you weren't sure and you wanted to give it a go, even though you didn't know if it did or not, you could write it out as this to start with, right? So we'd have t, and then we've had addition on both pieces. The other piece must have to be over t, which is fine. And what would be the numerator? They'd be 2's. Now, it's always the trick is whether we're getting the middle term. So check it out. If we take these 2 and we multiply, and they take these 2 and they multiply, and we add them together, will we get this middle term? And the answer here is yes. And so it's very friendly because the t in each of these denominators, 2 over t, cancels with the t you're multiplying by. So that's where the elimination of that variable is that's happening. And so this is very friendly. 2 in front, 1 to 3. So we have our integral from 1 to 3, and this is 2, and this is the square root of t plus 2 over t squared. And so what happens? Square roots and squares cancel, right? We need that square root to cancel if we're going to be able to integrate this by hand, because the u substitution step that we would need otherwise doesn't work because of the pieces where they are. So we end up with, let me put the 2 in front, and then I have t plus 2 over t. So now then, we're doing antiderivatives. So what's the antiderivative of t? T squared over 2. And then what's the antiderivative of 2 over t? Yeah, it's 2, and then it's natural log. It's technically the absolute value t. We're going to be putting in positives, so if you left it off here, that would be okay. Our inputs are positive 3 and negative. I'm sorry, positive 3 and 1, not any negatives. And you could distribute this 2 through. It would be kind of a nice thing to do at this point, simply because it simplifies well. So you'd have t squared plus 4 natural log of t, and then we're going to evaluate 3 and 1. So I have 3 squared plus 4 natural log of 3 minus 1 squared minus 4 natural log of 1. So I have 9 plus, you can write this as 4 natural log of 3. You could write it as natural log of 3 to the 4th if you wanted. I'm just going to leave mine as is. My 1 is fine. What's the natural log of 1? It's 0. So this piece still just disappears completely. So we would have 8 plus 4 natural log 3, or if you prefer, this would be 8 plus the natural log of 81. Okay, so does everybody remember how I get natural log 81? The power here, one of the properties of logs is that the power is the same as, the coefficient is the same as having a power, and 3 to the 4th is actually 81. So it doesn't matter if you do it that way. I just want you to recognize there is another version if you're looking at something and it's giving you a resource, right? Looking at other resources and it's giving you an answer that you're like, no, wait a minute. That's the same thing. Okay, what do you think? Not too bad. So let's just pause for a moment and consider what would have happened if we'd gotten to this point and there wasn't any way of factoring it. Well, we've encountered some like that. We'd have to go to the calculator and let the calculator do it for us, right? And your book tends to be pretty good, at telling you when you're going to be required to use a calculator and when you're not. And so same thing with WebAssign is they usually say give an approximation when they know it's not going to work. And if they don't say give an approximation, they're expecting you to be able to do it and to do it with radicals in the answer, and that's going to be an exact answer. Okay? Preston?
Do we learn how to integrate with hyperbolics?
It's not in Calc 2 or Calc 3, so perhaps in Calc 4, but I don't remember for sure. Yeah, I don't remember. Ready for the other half? So that's one half. Half of this is arc length.
So
arc length doesn't work much different, right?
So
Go ahead.
I just asked you, was I had to keep it that form and not plug it to the calculator to get its approximate value?
If it doesn't tell you to get an approximate, then I don't want an approximate, correct. And typically that's what WebAssign does too, is if it wants you to give an approximate, it's going to tell you that. Otherwise, it's not going to accept that as an answer at all, typically.
Okay.
Yeah. All right. Let's talk about what it means to talk about curvature. So let C be a smooth curve, either in the plane or in space. So you can talk 2D or 3D. Then the curvature, K, so we're using K for curvature because we keep using C for curve, okay? K for curvature at T is defined as the magnitude of T prime of T divided by the magnitude of R prime of T, or the magnitude of R prime of T cross R double prime of T divided by the magnitude of R of T, R prime of T cubed. Okay, so this is really going back to what we had done in chapter 12 that we've kind of let sit for a week and a half, right? That T of T is showing up in there. And the cross product stuff that we had seen before as well, back in chapter 11, I believe. Yes, sir, Dylan?
So that's R prime of T magnitude divided by R prime of T magnitude?
But it isn't, it's the cross product. Do you see that on the top? It's not multiplication.
I'm
on the top we have a cross product, so it's not going to just be able to be divided out, which I think is what you were thinking it looked like, right?
Yeah, it just looks like it goes
Yeah,
to one.
it doesn't work like that because we've got the cross product. And it's also R double prime on the top. And so we've got that going on too. Okay, you ready to give it a go? Okay, computationally, it's a little bit of a mess what we're doing, but it is just computation pieces. So take a look. We're going to find the curvature at the given point. Here is our R of t equation. And we're going to do R prime and we're going to do R double prime. Okay, that's how we're going to take this one. So we're going to take R and take its derivative. So what's the derivative? And we'll just do it in vector form, like in the coordinate form like this without the ijk, since this is how it's given to us. Derivative of t, derivative of sine 2t.
T goes to T.
And derivative of 3t. 3. Excellent. All right, and then let's do I meant to put prime there, sorry. Second derivative, so make sure your notation's not messed up because mine was. So the first one we just found was R prime of t, now we're doing R double prime. So what's the derivative of this one? Well, 0, and then negative 4 sine 2t, and 0. And we're going to be evaluating all of this at 0 because it tells you t is equal to 0. So over here, I'm going to find those values at 0. So R prime of 0 and R double prime of 0. So if I evaluate my derivative at 0, well, the 1 and the 3 don't change because those were constants to start with. It's just the middle term that I'm going to have to evaluate. So what is the cosine of 0? It's 1, and then multiply by the 2 in front to give me a 2. Correct. So I'm going to get a 2 on that one, right? All right, how about the next one? Well, I've got a 0 at the beginning and a 0 at the end. Those were constants to start with. What's the sine of 0? That one's 0. So I get the 0 vector on the second one. All good so far? Okay. So then we're going to find the magnitude now of R prime of 0. So we have the R prime of 0 over there on the right-hand side there. So I have 1 squared plus 2 squared plus 3 squared, which gives me the square root of what? 14. All right, so taking a look back at my formula, I'll flip back to that page in a second. I have found either the bottom denominator, right, of the first piece, or on the second piece, I've found the bottom, and then it would be that cubed value, correct? So in either formula, I've essentially I've identified what the value of the denominator is, correct? All right, we're able to find R double prime of t very cleanly, so we're going to do the top of the second half, the second side of this formula, and we're going to do the cross product. So let's see what you remember then about cross products. How do we find the cross product of R prime of 0 with R double prime of 0? How do we find the cross products? Yep, we made a matrix. And this is an IJK matrix with the ordered pairs. And because I've got, the valuation at 0, this is not so bad. I've got just numbers. So I have 1, 2, 3, and I have 0, 0, 0. So what's going to happen when I get this cross product? You probably know or anticipate it's just 0. Because every time when I'm expanding along minors here, so if I expand along this one, that means this 2 and this 3, they get multiplied by zeros, right? And I'm going to do that every single time because I'm always going to be multiplying by zeros on the bottom row. So as I do this cross product, and if you want to see it written out, you can, right? So we would do I, and it would be 2, 3, 0, 0, and then minus j, and it would be 1, 3, 0, 0, and then we can do k, and it's 1, 2, 0, 0. I get zeros everywhere. So this is the 0 vector. Agreed? 0 vector is what we had. But notice the numerator on the second half is asking for the magnitude of the 0 vector. Well, what's the magnitude of the 0 vector? It's 0, right? So the magnitude of what we just found is also 0. So k, the curvature, is going to equal 0, because that's the magnitude on top, divided by the square root of 14, which happens to be cubed, sort of irrelevant because 0 is on top, but it is cubed. And this curvature would then be 0. Okay, so there's no curvature happening at that point. Okay, so I wanted to show you one example where we worked it out with this definition of curvature. And then my second example is going to show this definition of curvature.
That
Sound
one's
good?
probably a lot easier though.
We'll see. So this one was really nice on this one because my second derivative and cross product, we had lots of zeros showing up. So it was very friendly to work with that way. It wasn't bad. But there are situations where one's preferable to the other, but you can use either one of them that you choose. Okay, so here's our second one. This is a plane curve, right? Because it's just 2 dimensions as opposed to 3. But remember, curvature's definition worked for either one. Okay, so it's okay that it's 2 dimensions. That'll work just fine. Either way, I need to find the derivative. So let's do that. And we'll do it in the IJK, or in this case, IJ format, because it's given to us that way. So what's the derivative of 4 cosine of 2 pi t I?
Negative 8 pi cosine, or sine t, or 2 pi t.
Yeah, you got it all. Okay, negative 8 pi sine 2 pi ti. How about the other half? 8 pi cosine 2 pi tj. Do you notice there's something missing from this one that the other one had besides the fact that there's not a k? What else is missing?
Where you're at.
Yeah, it doesn't give me a t value, right? That's not friendly. Without a t value, we have to leave it arbitrarily in terms of these values the whole time. Do you recognize that? Okay, so I want you to keep, so pay attention to that nuance here that's happening. We do need to find, either way, again, the magnitude of this, whether we have numbers or whether it's arbitrary like it is, we're going to find the magnitude. So the magnitude is to take each of these and square them now. So I have negative 8 pi sine of 2 pi t squared plus 8 pi cosine of 2 pi t squared. Now, a good portion of this is going to clean up really nicely. So I've got 64 pi squared sine squared 2 pi t plus 64 pi squared cosine squared 2 pi t. It is, yeah. So can you lead us how you got there, Dylan?
Sine squared, cosine squared is equal to 1.
Okay.
But before you do that, you pull up just multiply squared.
Okay. So when we see sine squared plus cosine squared, which we had one like this on the last example, and I moved too quick and I made a mistake, and so it was messing things up at the end. Y'all remember that? And I recorded a short video to fix it. Well, we'll do it right here. So Dylan's exactly right. We're going to pull out the coefficient part that they have in common, which is the 64 pi squared. And it actually can pull clean out from underneath the radical. So the square root of 64 is 8, and the square root of pi squared is pi. And then what that leaves us with is exactly those yellow pieces that I've marked, sine squared 2 pi t plus cosine squared 2 pi t. And that's a Pythagorean identity, right? Everything that's underneath there is equal to 1. Square root of 1 is 1. We end up just getting 8 pi. We're not done with the problem, okay? Hold tight. All we've done is find the magnitude of the derivative. That's all we did so far. But that's part of it, right? And in fact, it's kind of friendly. I don't have any variables left, right? That is a constant. So that's a good thing. We're going to find capital T of t next. All right, so taking a look at capital T of t, we will have, let's see, I don't have a lot of details written in. So this is the, okay, hang on just a second. Okay, so let me write in from 12.4, since we've had a break from it, what the formula is for T of t first, and we'll write it in right here. So T of t is R prime of t divided by the magnitude of R prime of t. So we have both of those components. So our R of t, which was originally given, R prime of t, which we originally found, which is negative 8 pi sine 2 pi t I plus 8 pi cosine of 2 pi t j, and it all needs to be divided by 8 pi. So we can do that. It's very friendly. It eliminates just the coefficients in front. So negative sine of 2 pi t I, oops, that's supposed to be a t first, t and then I, and then plus the cosine of 2 pi t j. Okay, so that's t of t. All right, so taking a look back then over here, it says the next thing we're supposed to do is we're supposed to, well, the whole numerator of the first piece is the derivative of what I just found. Okay, so that's where I am at this point. I found t of t. Now I need to find t prime of t. So I need the derivative of this. Slow down just a little bit. So what's the derivative of negative sine 2 pi t I? Uh-huh. Okay, so look okay? And then how about the derivative of cosine of 2 pi tj?
Negative 2 pi.
Yep. Negative 2 pi sine 2 pi tj. Alrighty then. And we're supposed to find the magnitude of that, correct? So we need the magnitude of t prime of t, again, arbitrarily. So we have the square root. We will have negative 2 pi cosine of 2 pi t squared plus negative 2 pi sine of 2 pi t squared. I don't have any space over there. Let me just shift this over. All right, so the first piece ends up giving me the square root. We have 4 pi squared cosine squared of 2 pi t. How much space do I have? All right, well, I'm going to have to just try and do what I can. Plus, and then I have 4 pi squared sine squared of 2 pi t. And this looks familiar, right? It looks a lot like the other piece. What will this become? It'll be 2 pi. So, but just like the last time, and we won't write it all out this time, but these two pieces right here will be grouped together. If I pull out the 4 pi squared, pulling them out of the radical entirely, that will become a 2 pi. And then I have the square root of a Pythagorean identity. The cosine squared plus the sine squared is equal to 1. So this is 2t. 2 pi, which is going to say 2 pi. And then our curvature is supposed to be the magnitude of t prime of t divided by the magnitude of r prime of t. And these were very friendly values, right? I actually got 2 pi for the top. I have 8 pi for the bottom. What does the curvature end up being? It's 1/4. And so I get a 1/4 at the end. Obviously, if things don't collapse very nicely, we could still end up with some radicals involved, right? These functions were fairly friendly to do this with because of the way that they were structured, right? They both had a 4 coefficient to start with. They both had the same angles in the middle. I had one sine and I had one cosine. So there's a lot of pieces that actually played into making that work out nicely.